What we're interested in is studying government policies that have the feature that they continue in force unless there's new action that takes place. So this is the endogenous status quo. We've heard about that already. The kind of feature that I want to point out is that these policies seem relatively stable over time, even though they could be changed at any moment. So we want to explore both the nature of the policies when the status quo remains in place, if it's not changed, and we want to see if stability is predicted in equilibrium. So the research questions we're going to ask is, in a dynamic political model, which coalitions are going to form and which policies do they support? Are these stable? Can the theory explain things like universalism and surplus coalitions, which are hard to explain in some kinds of legislative bargaining models? And for the conversation with Steve in the bus yesterday, I think they can also explain minority governments in a particular way. Can these policies be inefficient, or are they all efficient? What's the relation to sequential or static legislative bargaining? And are these dynamic coalition equilibria robust to shocks and crises? So the first thing I'm going to do is just informally say what we mean by dynamic coalition. So you notice that I intentionally didn't mention that this is a paper with Renee. And since she doesn't mention bullying when she makes her presentation. But anyway, this is a joint paper with Renee, obviously. So informally, what we mean by a dynamic coalition is that there's a decisive set of legislators, all of whom strictly prefer that set of decisive legislators continues from one period to the next. Okay, so that's what we have in mind. We'll formalize that in just a minute. So the perspective here is we'd like to study the existence of dynamic coalitions and the policies that they support. We'd like to do it where it's hard, so we're going to do a pure distribution model. We want there to be lots of opportunities for changing this policy, and we're going to study this with the Markov perfect equilibrium concept. Now this is going to be theory, so I'm going to do theory, but then I'm not going to motivate it anymore. But at the end, and I'm going to try to go fast enough to get there, I'm going to talk about numbers, update it, and application. So that comes at the end rather than the beginning, since you need to see the theory first before it makes any sense. Okay. So we'd also like this to be kind of a simple model that can be readily extended and be used for other purposes in addition to what we've done. So here's a preview of some of the results. First of all, policies and coalitions, they exist and they're stable. And this existence can be established using only current period information, even though it's a dynamic model. And these dynamic models, or these dynamic coalition equilibria that we're going to characterize, are not ones that just exist for delta close to 1. In fact, delta can be as low as 0, or almost 0, and still have these equilibria established. Now, we'll show that. These coalitions can be minimum winning, surplus, universal, efficient, and inefficient. We'll try to understand that. Within the coalition, the allocations could be even, and we'll look at that case quite a bit. But they can also be uneven, and we'll talk about that. The legislators who are not in the coalition can also have positive allocations in this model. It's also the case that a policy could be supported in equilibrium even though it would never be proposed by any legislator in a coalition formation stage of the game. And we'll see that we have an interpretation in terms of vested interests that are vested in the status quo, and that can be then supported as an equilibrium. We're also going to look at the case in which there's going to be implementation uncertainty. So there are going to be shocks, and we're going to try to characterize equilibria that are present when there are these shocks, and then we're going to ask the question, suppose this dynamic coalition tolerated shocks, let's say small shocks, but didn't tolerate large shocks, like crises, for example. There is a related literature. It's here. I'm not going to say anything more about it, but the thing that's interesting about this is the dates. Almost all of this has been written within the last 2 years, let's say. Okay? I don't want to say anything more. There's been a burst of activity in this area. All right, so the organization, I'm going to talk about the basic model. I'm going to talk about implementation uncertainty. I'm going to talk about some data from the Bettolini and Palfrey experiment that is actually an experiment with exactly this model, and talk about an application. So here's the basic model. So this is going to be legislative bargaining. There's an infinite number of periods. There's n members in this legislature. There's a majority rule that's any m greater than or equal to n plus 2, but not unanimity. It's a pure distribution model, so we're going to divide 1 unit of goodies in each period. We're not going to explain where that comes from. It's just available in each period. So we're going to be able to allocate that in any way we want, efficiently or inefficiently. So it's a simplex in the interior. There is a status quo or state variable in this model. The state variable is going to be denoted by Q, so there's a state variable at the beginning of the period. Agenda formation here is that in each period there's a legislator that's selected to make a proposal, and there's only one proposal per period, but there are an infinite number of periods. So there's a status quo, and there's going to be proposals made in each period. So there's going to be a vote between the status quo and the proposal, so that's the agenda. Okay? And whichever wins becomes the status quo for the next period. So it's a very simple transition. The equilibrium concept here is Markov perfect equilibrium. So the state variable is just the status quo. Everybody knows what that is. And what we're going to do, the thing that I really want to show is what the strategies that we're going to consider. So these strategies are what we call basic strategies. They're very simple. And what they involve is the following. So here we're talking about basic strategies. So what do they look like? So we're going to start with some set of policies, we call it capital Z. These are the ones that will be supported in equilibrium. What the strategy is, so sigma was on a previous slide that was in the dark, so you didn't see it well, is the proposal strategy. So if the status quo is in that set of supported policies, then we're just going to propose the status quo. If it's not, we're going to propose something that's good for us, that is, we as the proposer. So that's going to be a set defined by, I didn't touch anything, defined by ZI, is a set of things that are good for legislator I. And those are the ones over which legislator I is going to propose, and it's going to be randomized. Okay? Voting strategies are going to be stage undominated. So that simply means you vote for what's best. If it's strictly best or worst, you vote against it. And our indifference rule here is that you vote for the status quo when you are indifferent. So the logic of that is, if you have this coalition that you wish to preserve from one period to another, what you want to do is just vote down something that looks equivalent, okay, but maybe isn't. Okay? So we'll talk about that more. I've got a slide. So the preferences are coming up on the next slide, okay? And so the one thing I want to point out about basic strategies is, remember, if the status quo is in this set capital Z, you propose it. And that may be bad for you, but you're willing to propose it anyway, because anything else that you propose would be defeated, okay, in the vote. Okay? So this is kind of a modeling or setup simplification that actually is quite convenient. Let's put it that way. All right, so let me continue with the setup here. Okay, so we're going to start with a set of policies, and that set of policies is going to be denoted by S. So that's kind of the primitive here. And we want this to be a model where there's no favoritism of particular legislators. So what we're going to do is we're going to look at all of the permutations of that set S. And that's what this set capital Z is going to be. Okay? So that means ex ante, every legislator is treated alike. They have the same opportunities available to them. Okay? So for example, if S is equal to a half-half 0, then the set Z that we'll be talking about generated from that is just 1/2, 1/2, 0, 1/2, 0, 1/2, 0, 1/2, 1/2. Okay? So these are symmetric sets. What that means is that set ZI of good things for legislator I looks just like the one for legislator J, okay, which helps in the specification as well. So if you think about the basic strategies, what they call for is proposing the status quo when it's in Z. So what that means is, if everybody were playing these basic strategies, that status quo point would be an absorbing state. So what that means is the continuation value is just the utility So somehow I missed the slide in the darkness about what utility functions look like. So we're maximizing the sum, infinite sum of utilities. Everybody has the same utility function. Okay? By the way, I should say that we're going to present this for a bit simpler model than is actually in the paper, because in the paper we allow discount factors to be different and recognition probabilities to be different. They're going to all look the same in this presentation. So the continuation value is just what you get from that policy in Z that stays in place thereafter. If everyone plays these strategies, then it's an equilibrium divided by 1 minus delta. And the continuation value, if you propose something that's not in Z, is just now whatever the next person who's recognized is going to propose, and they're going to randomize among all the elements of this set, Zi, all the things that are good for them. Okay? All right, so what that means is that the continuation value, which we denote by V star, is just the average of all of those utilities that individuals would have, and it's all going to be the same for everybody because these sets are symmetric. So it's just the average utility of what you would get from randomization with proposals from this set Zi. Okay? We're going to call that U bar. Now, what do we mean by, so here's going to be the formal definition. So first of all, a coalition equilibrium is just a Markov perfect equilibrium using these basic strategies. And a coalition, a dynamic coalition, so we're thinking about a coalition equilibrium supporting the set Z, and the dynamic coalition is that set of legislators who have a continuation value, that's this VI of QT, greater than V star. Okay? Now, in the next slide, I'll analyze that, so we'll see what it actually means. Okay, so this is just in words. So one way to think of it is everybody in this dynamic coalition wants the coalition to continue. The other way to think about it is if the coalition didn't continue, all of these people would be punished by the new coalition, in expectation by the new coalition formation stage. These things are formed in the first period. There's no delay. It persists. And there's one of these dynamic coalitions corresponding to every policy in this set, capital Z. First of all, if we want to look at that definition and break it down, remember we've got an absorbing state if you're in cap Z, and if you're not, you get this average of the utilities of everything that would be proposed. And so both of these then, that is this VI of QT greater than V star, and I don't dare touch the pointer here, is simply comparing two kind of current period pieces of information. Okay? So that's a key feature of the equilibrium here. We'll see that in more detail in just a minute. Okay, so this is actually a static comparison when we look at what the dynamic coalition is and who is in it. So here's the example. N equals 3, M equals 2, linear utility functions, and this set 1/2, 1/2, 0 that we had before. So the V star is now 1 over 3, 1 minus delta, okay, because there are 3 players. Just think of it as symmetry, for example. And here's the absorbing state that we had before. And what we want to do is we want to just prove that this is an equilibrium. Okay, so the proof goes as follows. Let's look at a tempting deviation, which is 1, 0, 0. That is, if Q0 is that, I, as player 1, could just propose it, and I would get 1. Okay? And what that means is, if I did that, I would be deviating, so I would get the 1 plus the continuation value V star. And if I went to the equilibrium proposal in the supported set, I'd get 1 over 2, 1 minus delta. Okay? So the question is, well, when is that deviation not attractive? Well, it's not attractive when that continuation value is less than 1 over 2, 1 minus delta. And what that means is whenever delta is greater than delta bar equal to 3/4, this kind of a deviation is not attractive. Okay? Now there's another kind of deviation which is within the set Z, big Z. So it could be that we've got a coalition between 1 and 2, and player 3 comes around and offers an equivalent deal to legislator 2. Under our indifference rule, you vote no. Okay? That can't be any better. Okay? And you have an interest in preserving this coalition. if you like to think about kind of forward-looking, suppose everybody was tempted by one of those alternative proposals in the set capital Z. If that were the case, then indeed the continuation value couldn't be 1/2 divided by 1 minus delta. You have to be 1/3. So this indifference rule is, we think, kind of natural in this dynamic model, because the idea is with a dynamic coalition you want it to continue. And this is a way in which it continues against kind of equivalent, apparently equivalent offers. Okay? If you didn't use this, then the kind of equilibrium you'll get is like the Coulomb-Dracos rotating dictator equilibrium. And I should point out that at least one of our co-authors, or discussants coming up, has actually used a rule that has this feature as well, Tom. So here are some corollaries of the proposition that corresponds, general proposition that corresponds to the example that I did. These dynamic coalitions can be associated with both efficient and inefficient policies. I'll show some examples of that. Dynamic coalitions can maintain these positive allocations to legislators who are outside the coalition. So we'll have to talk about how do we know who's in the coalition, how can we tell? And these dynamic coalitions can have surplus members as well. So who's in the dynamic coalition? So if there's only 3 players, 3 legislators, there can only be 2 in the coalition. So this bottom example, I won't go through this because we don't have enough time, but I'll tell you what it says. So this is an n=5 case. And the allocations are, you get big allocations, C, to 3 players, something less to the 4th player, and something less to the 5th player. So the question is, who's in the dynamic coalition? Well, the 3 getting the big share, by the way, this is simple majority rule. The 3 that are getting the big share are clearly in the coalition. What about the 4th guy who gets this amount A? Well, the answer to that is, this player is in the coalition if A is high, and not in the coalition if A is low. Okay? So what's the intuition of that? If A is high, this player wants to preserve the coalition so it continues into the next period. If it's low, this player wants the coalition to be dissolved because a new coalition opportunity will pay off more. Okay? So one way to think about this is that this is a junior member. This is somebody who gets strictly less than the other ones, but is still supporting the coalition. Okay? So Steve, in a government formation case for minority governments, you could think of CCAAB, and if the A is high enough, then there is a dynamic coalition that has 4 members, but there are only 2 of them that get the big allocation. If you want to think about those as the government and the others as the supporters of the government, okay, that would be one interpretation. So let's talk about existence in this model. So now we're going to be more general. So the first thing we want to do is define a set W of Z. So W of Z is, we're going to look at a policy, little z and big Z, and we're going to ask, what are all of the policies in big Z that are majority strictly preferred to Z? Okay, and we're going to call that thing W of Z. So that's kind of like a win set, if you've ever seen that kind of terminology, except now we have strict preference. Okay, and we're also going to look at kind of who's the most vulnerable member of this coalition. So we're going to look at the nth smallest allocation in any of these policies that are in this set S, and we're going to look at the minimum of all of those across the legislators. We're going to call that Z sub M min. It's a terrible notation. We have to do better than that. And what's the proposition? The proposition is that a Z generated from some S, okay, can be supported as a coalition equilibrium if the discount factor is high enough. There's an expression for it. We'll talk about that in a minute. And the 2 conditions are, 1, that this W of Z is empty. That is a set that's empty. There's nothing that can defeat any element in the set capital Z. Okay, so that's like the second part of that 1/2, 1/2, 0 example that I did. And the other part is that at least a majority of members of the legislature will be punished if this coalition dissolves. Okay, so that's like the first part of that 1/2, 0 example. So I have a logic of the proof, but the logic of the proof is just like the 1/2, 0 case. So if it's okay, I just won't present that and we'll move on. But it's the same exact logic as what we had done. What about the discount factor? So this an issue is, this is in a group of people who are interested in politics. The question is are discount factors of politicians high or low? Okay. So some would argue, well, they're high, but others would say they're low because it's political leaders that are anxious to be in office, in government, or whatever. And the minimal discount factor associated with the proposition about the existence of these coalitions looks like this. Here's that thing that we looked at, kind of the most vulnerable member. Here's what you get, Gary, if it's 1, it's the best you can get. And this is the difference between what you get with 1 and the randomization part. And this thing, think about U being strictly concave. So you can think about this thing getting bigger, and as it gets bigger, delta double bar, lower double bar goes down to 0. Okay? So this would say if politicians are very impatient or very risk averse, then this model could be applicable to let's say a variety of settings, let's put it that way. This is a slide that makes the following point. This set Z, you can think of this as being composed of 2 kinds of policies. One set of policies is the ones that people would propose when there's a coalition formation opportunity. That's at ZI. Okay, so that's kind of natural. Those are the things that are good for the proposer. But there can also be elements of this set, big Z, that are supported as part of this coalition equilibrium that no one would ever propose. So what we're thinking there is, think about these as interests that are vested in the status quo. And they could form a dynamic coalition that would support one of these elements. Okay, so there's an example down here. These things can actually be Pareto dominated and still be supported as part of the coalition equilibrium. And the rationale for that is there is a decisive set of members who are willing to have that policy and the coalition continue from period to period. Let me skip that. So we're going to look at the case of n equals 3. And the kinds of coalitions that can form there are only of one type. That is, there's a 2-person dynamic coalition and they both get exactly the same thing. And a third person could get something less than that. That would be what causes V star to be less than V of QT minus 1, or QT. Okay? So these things are always minimal winning dynamic coalitions. They can be efficient or inefficient. Okay? And it's also the case that the universal allocation, where everybody gets a third, can be ruled in. So now let's go to Tom's question. So the question is, how can 1/3, 1/3, 1/3 survive when 1/2, 1/2, 0 is available? Well, 1/2, 1/2, 0 isn't available, then it could be supported, and it needs a threat, so a threat would be 1/3, 1/3, 0. So this notion about a dynamic coalition being punished can be thought of as, if there's a threat of some policy that's bad, okay, that can support a coalition. Okay, so here, for our n equal 3 case, this is the set of efficient policies. It includes the universal allocation. This includes the von Neumann-Morgenstern stable set. But this 1/2, 1/2, 0 could in fact be defeated by all policies in Z if it didn't start out in Z, okay, in a coalition equilibrium. So now what we want to do is we want to have implementation uncertainty. So the idea here is to ask 2 kinds of questions. The first question is, are these equilibria robust to shocks? And the second is, if we do have these shocks, is the allocation within the coalition different from 1/2, 1/2, or CC and something for the third guy? So those are the 2 questions. So we have in mind these shocks are things that could be completely endogenous, they could be exogenous, They could be endogenous in the sense that a policy gets implemented and people on the ground then make their actions, and it's hard to forecast exactly what those actions will be, and there's some uncertainty there about what happens. So the uncertainty here affects current period payoffs and the transition to a new state. Okay? So if you want to think about this kind of uncertainty, think about implementing Obamacare, trying to think about what the outcome will be. So we'd like to model this uncertainty in a way such that we can do some comparative statics. So we're going to do it in two stages. One, there's going to be some probability that there'll be a shock, and then if there is a shock, there's going to be the magnitude will be some continuous, we're going to assume it's uniform distribution. There's a probability eta that there's going to be a shock. Now we also set this up so that the shock could be more likely if it's a new policy relative to an old policy. So that is an existing policy. So the existing policy has a probability eta of having a shock, and a new policy has a probability gamma. We're going to assume that eta is less than or equal to gamma. There are supports for these shocks in terms of their magnitudes. Those are represented by theta under bar and epsilon under bar. We're going to assume that the magnitude of the shocks for a current policy could be less than the magnitude of a shock for a new policy. The transition looks like the following in the payoffs. If we have a policy that gives 1 minus C to the originator of a coalition, where C is less than half, the partner gets C, and then there's a shock minus theta T. Okay? And that is going to produce then, and the originator of the coalition gets 1 minus C plus theta T. Okay? So that's the transition and the payoffs in current period T if there is a shock that occurs. In this example, so what we're going to do is we're going to try to look at policies 1 minus C, C0. We're going to ask is whether C can be strictly less than 0. Okay? And we want to ask ourselves what's the probability that the coalition dissolves because of the shock. Okay? So those are the questions. And so let me just go on. So in this model, what we're going to have is that policies that are like this point, and that point can be supported as part of a coalition equilibrium. Also policies that are this point, and this point can be supported. So there's some set that are bound on this C, how low it can be. If it gets too low, if the allocation of the partner gets too low, the partner's going to defect. Okay? So there's going to be a bound. And the trick here is to characterize the bound. And the proposition is the following. If delta is at least as high as this more complicated expression now, and the uncertainty isn't too big, then indeed there is this bound that's strictly less than 1/2. And that bound then says that there's a whole class of these, what we call specific policy coalition equilibria, where each one of them is characterized by a value of C that sits in this interval. Okay? And the proof of this is basically kind of brute force. Check all of the deviations and find out what these bounds are from the incentive constraints. Find out when those bounds are strictly less than 1/2, which is when delta naught is less than 1. And delta naught is less than 1 when the uncertainty is not too big. Okay? So that's all I want to do about the argument there. So I'm going to skip the proof in steps. The characterization is exactly as you would expect. The higher is delta, that is, the more patient are the players, the larger is the set of allocations that can be supported in equilibrium, exactly as our intuition would tell us. So now we want to ask, so by the way, these coalitions fail whenever there's a shock, right? Because whenever there's a shock, what it means is there's going to be a draw from a continuous distribution. The probability that the draw is 0 is 0. And therefore, these things always fail when there is a shock. And that happens with probability eta. Now, I should say if eta is equal to gamma, then basically this is the same model that we had before, where the allocations are simply even division within the coalition. Okay? So it's the lower uncertainty associated with current policies that allows a disparity in allocations within the coalition. So the question is, how big is this set? So we have a characterization of this tolerant coalition equilibrium, complete characterization for the case in which there's uncertainty associated with new policies rather than old policies. And what I'm going to tell you about that is nothing, because I got the sign. So let me say something about experiments. So Marco and Tom have done an experiment on exactly this game, okay? They do two experiments, one where there's a finite set of alternatives and one where there's the same set X that we use here. And what we've done is we've sort of looked at what the outcomes of that are. And what I want to do is I want to talk about that, okay? So coalitions of the type 1, 2, 1, 3, and 2, 3 in the discrete case where there's, remember, the only alternatives here are the universal allocation and minimal winning coalitions where you divide the entire set of goodies, 60 in this case, between two players. So the probabilities of transition are 0.77, 0.79, and 0.75. So that's, my view is that that's not inconsistent with the theory that's presented here. So we also looked at what the duration of coalitions were. So here's an example of, so there are three sets of 3 players here. This game lasted for 8 periods. 2 coalitions lasted the entire 8 periods, and 1 lasted 7 periods. Okay, so that's dead on to what this theory predicts. Unfortunately, a lot of the others don't predict that. Okay, there's churn. Coalitions get started, they fold, they get started again, and continue for a little while, and then dissolve. So the point of this exercise of looking at these tables is the evidence is underwhelming. Okay, so let me continue. We also looked at the continuous example, the continuous case, and these are transition probabilities, and you can see again the same kind of pattern. If you're a 1-2 coalition or allocation, you tend to stay there, and the same is true for the others, though it's less true for M2-3. I have no idea why that's so low. It's also the case that the universal allocation is supported here as a coalition, okay? And our theory predicts that. So our theory predicts the universal one, as long as there is some other threat that's available or possible within the system. So this says the following. So the way to think about their experiment is that these are players who are on islands and they can't communicate. Okay? And if you think about if you've looked at these sequential bargaining models where they do experiments, all of those experiments find only weak support for the Baron-Fairjohn prediction. Okay? But again, those are island theories. So Marina Agranoff and Chloe Tergman did an experiment. It's exactly sequential bargaining, where after the proposer makes a proposal, there's a communication period. Cheap talk can be engaged in by all of the players in the experiment. And all of a sudden, the play of the participants in the experiment go almost exactly to the Baron-Fairjohn prediction. So the question is, suppose we had a future experiment where we did exactly what you did, but now okay, 1 minute. So now what we do is we allow communication. So now the question, so this gets to your point earlier. So now the question is, what's the prediction here? Okay? So, so one argument would be, well, 1/2, 1/2, 0 seems focal in this case. Okay? That is, you can imagine a proposer making a speech. I'm going to make a proposal where we're going to divide the dollar between us, and we want to sustain that over time. We can never do better than that in this game. And there are other arguments that are speeches that could be made, but that's basically the speech that it seems to me that kind of supports this. Now the question is, will this be supported by an experiment, the outcome? And an experiment like that maybe in the future. So this is the application. So one of the problems with sequential bargaining theory is it's kind of has a harsh prediction regarding what kinds of governments might form in a multi-party parliamentary system. This model, okay, predicts all kinds of things, okay? Now, it doesn't predict everything, but it predicts lots of things, okay? And so let me go to this is the last slide. There is nothing more beyond this. So this theory would say, for example, well, governments could be formed even though political leaders are very impatient. These governments could tolerate shocks, but they couldn't tolerate large shocks, okay, because those are going to cause such uneven distributions within the coalition that it won't be stable. You think of those as crises. The theory tells us something about why and when governments fail. It also tells us something about when governments cannot form. That is, if there's one of these status quos that's supported by these vested interests, there can be no new coalition that forms. So if the government fails, it's one of these policies. So you might think about this as Belgium, for example, in recent times. Okay, nothing can happen. Okay, there has to be an election or something else. It also predicts both efficient and inefficient policies. So these vested interests could support a policy that's inefficient. Inefficient in the small n case would simply be that exactly what we were talking about. There's some allocations that don't add to one, but it could also be Pareto dominated in a larger legislature. Okay, and I guess what I would say is that most things really can't be supported in equilibrium. They can't be defeated by anything within Z, and they have to be such that there is a coalition that would be strictly punished if the coalition failed.